Yeah, I'm going to talk about the likelihoodAsy package. And this is a joint work with Don Pierce. And that's the recent picture of Don. So that's the outline of my talk. I'm going to give some limited background about likelihood asymptotics. And then we'll talk about the package. And I will illustrate its usage by means of two examples. So some words about likelihood asymptotics. It's a stream of research that was started in the 1980s by several researchers. And there are some recent reviews about, such as the book by Tom Sebrini and a review paper by Ipskovgad. And Don and I, a couple of years ago, we published a paper that tried to make the theory more accessible to a wider audience. And the paper came with a accompanying R package, which is called likelihoodAsy, which is available on CRAN. And it implements some of these methods. And some setting of interest and notation, well, the setting is very general. We assume to have some data Y of size n, that they come from a certain fully specified parametric model with parameter theta. And so L theta is a log likelihood function, and theta hat is the MLE, the maximum likelihood estimate of the parameter. And well, there are several methods, but the main methodology we are concerned today, it's about inference on the scalar function of the parameter denoted by psi of theta. And in particular, for testing the psi of theta is equal to psi, we rely on the directed deviance, which is the square root with sign of the likelihood ratio test. And so we have here the log likelihood drop passing from the MLE to the constraint estimate of theta when psi is fixed to the certain assumed value. And that's asymptotically, R is asymptotically normal with first order error, standard normal. So a key theoretical result is the so-called R star formula, which is an approximation to the distribution of R. And this is given by so the probability that R is less than the third value can be approximated by the standard normal CDF evaluated at a certain statistics R star. And R star is a modified directed deviance that was introduced by Barton-Linsen in a Biometrica paper. And this provides very accurate confidence intervals and tests. So the resulting accuracy is very close to the most accurate parametric bootstrap method, but there's no need to any additional fitting. So some brief comments about the nature of R star. The R star formula is derived from the P star formula, which is a formula for approximation to the distribution of the MLE given an auxiliary statistic. And the auxiliary statistic itself is a notional quantity. It makes the MLE to be approximately sufficient. And well, sufficiency gives you inferential optimality. And the R star statistic derives from the transformation from the distribution of theta hat to that of R. And well, our expository paper has a full account of these steps. So the key parts of the package, well, a major feature of the package, and perhaps the most important, is to implement the calculation of R star, which is rather challenging. I will say that the key parts are probably these two. First of all, the package implements the R version, which is due to Ipskovgad. And that requires the computation of certain expected values. And the package does this by means of some Monte Carlo computation. That's a pure Monte Carlo, no additional fitting, no bootstrap. The second step is the computation of the constraint estimate of theta, which entails this optimization problem. We have to optimize the log likelihood function under the assumption that the function of interest is equal to a given value. And here we endorse the augmented Lagrangian method for numerical optimization. And we take advantage of some existing packages such as R, Sol, and P, and Alabama. Okay, let's see how the package works. Well, it requires that the users supply two functions. One function to evaluate the log likelihood at a certain parameter value, and a function that generates a sample under the assumed model. The second one is required for the Monte Carlo part of the computation. And then it's useful, although it's not compulsory, that the log likelihood gradient is provided. Otherwise, the numerical differentiation is used. Okay, the first example here is about wildwood regression. So we have a sample of n observations from a wildwood distribution with this, the usual form for the survival function, the proportional hazard form. And the parameters of this model are given by gamma, which is the shape parameter, and a vector of beta coefficients that enters the relative risk. So altogether, theta is given by beta plus gamma. And we take psi here, the parameter of interest, as the log reliability at a certain time t naught for a given covered vector x naught. So that's the expression of the function of interest here. First of all, we have to define two functions, as I said before. And that's the function for the log likelihood. So theta here is a vector of parameter values. And then there is another argument required, which is called data. And data is the list that must contain all the information you need to specify the model. In this case, data as the vector of responses y plus the design metrics for the coefficients. And the rest is just standard wildwood computation, I would say. The second function we need to specify is the function that generates a sample. So it has the same argument as the previous function. And it takes the data, and it provides a copy of it with a response variable replaced by simulated vectors from the assumed model, where the parameter is given by the first argument. Okay, let's see an example of this with a data set. We take here a very simple data set from the math package. And we need to define here the list of interest, which is given by this list here. We have to specify design metrics, and this is obtained by the model.metrics call. That's a very simple model with just one predictor. And then y here is the vector of times. Then we define here the function of interest. That's just the R translation of this expression here, where we fix t naught and x naught. Okay, then the main function of the package is called R star. And here we just specify a certain value psi, for example, log 0.03. And that's the way we call the function. Well, the arguments are essentially the two functions we defined beforehand and the function, the value for the function of interest. That's what the summary function will return. Well, we get here the MLE of the function of interest with the standard error, and then some other information. And the most important one are the values of the R and R star statistics, along with the values of phi of R and phi of R star. So that's the R star formula I was mentioning a while ago. Perhaps more useful is the rstar.ci function that computes confidence intervals for the parametric function of interest. And well, it has also a summary and the plot functions for the resulting object from the code. Well, the list of arguments is similar to the previous function, although we don't have to specify any specified values since confidence intervals are of interest here. That's the summary for the object. And here we have 90, 95, 99% confidence interval based on the first order, which are the usual intervals that ordinarily used, but also the second order ones, which are more accurate. And then there are the plot method for that. That will return a so-called profile plot, or profile plot, since there are two of them. And well, for a grid of values for the function of interest, in this case is the log survival function, it will return the value of r as a function of psi and r star as a function of psi. Good. And here we can see, so we can obtain confidence intervals of all levels that can be read off the plot. And here we can see there is a notable adjustment provided by the second order method. As a second example, something still simple, but that entails something more elaborate, like logistic regression with the random intercepts. So we have the usual specification with the linear predictor and random intercepts, which are normally distributed. The log likelihood function requires we integrate the random effects out. And this can be done, for example, by using Gaussian quadrature. But here we use instead the TMB package, which is a very powerful package for automatic differentiation. Essentially, you write a C++ template for the log likelihood function, or minus it, the log likelihood function. And then the TMB package will return a C++ implementation into R, and then the gradient of it. For random effects, can also carry out the integration of the random effects via the Laplace approximation. And this is the C++ template we need for this example, which is very simple, and perhaps it's useful to have a look at the data part. We have to provide the number of groups, the group size, the response, and the design matrix. That's all we need. Then it's very easy to write down. And well, a call to make a defun function of TMB will do all the job, in the sense that the log likelihood function and the gradient are just obtained from the function. And here we apply this to a simple example. It's a multi-center clinical trial with one treatment indicator and random effects for clinic. It's a famous Bater and Landis data set. This is the part where we define the data list function, where we have to be careful in defining the object required by the TMB function. After you do this, you only need to supply a function to generate a data set. And here we can recognize the generation of the random effect and the generation of the binomial response. We can apply this, taking in turn as a parameter of interest the treatment indicator and the standard deviation of random effects. And we obtain that for the treatment indicator, the first order methods are very accurate, so there's no need to do anything more sophisticated than that. Instead, you get a substantial adjustment for sigma. It's essentially a degrees of freedom adjustment. Okay, so in closing, I would say that likelihood-Asy makes some arcane inferential methods readably accessible and is a handy alternative to bootstrapping. Currently, there is some support for modified profile likelihood for multidimensional psi, but this could be improved. And we would like to have some further function for constraint optimization, which is really important. And also, I think the better integration with the TMB package will be helpful, although it's already easy to do it. And well, that's the reference. And this is the expository paper I was mentioning at the beginning. It's published in International Statistical Review. And well, and those are the R packages that I mentioned. As I said, we rely a lot on these two packages, the Alabama and RSOL and P for constraint optimization. And I thank you for your attention.
Thank you very much.